what's a streaming database? It's a this and a that and a what. I'm going to give you a very specific thing that I'm going to use for the talk that we at Materialize think of as a streaming database. Foremost, it is a database. Streaming modifies database. So it's a database for Materialize, a SQL database, and you do standard SQL databasey things with it. You connect to it, you say, I'd like to create a table, I'm going to insert some stuff into the table, I'm going to run a select statement to read stuff back out of the table, I'll create some views, I'll create some indexes, all of those sorts of things. But everything I've just described is very pull-oriented. You ask the database to do a thing, it does that thing for you. It responds to your commands, and that's the basis on which the database takes action. A streaming database is a modification to such a database where there's some sort of framework for the database to leap into action on its own, to do some work on your behalf, anticipating potentially what you need to do, but some way that you're able to communicate to the database, hey, you should go and do some work, potentially when the data change rather than when I ask about the data, to prep some work for me. And that's the direction we're going to be heading. That's what's going to be exciting about a streaming database is this new dimension of when does work get done. So a bit more specifically and with some concrete examples, we'll build this up. The thing that I want you to think about with the streaming database is that users get to trade off when work happens. There's two, roughly, times that work might happen, either as data are ingested or when a user asks a query. These are two times that work could go on in the database, and a user gets to control this. They get to decide or guide the database as to when this work should occur. And the way to think about this that I think is easiest, there's two commands. They're pretty common in SQL. People use them a lot. And they guide the database as to when you would like the work to happen. So we have create view and select. Probably a lot of you know select. Here's a query. I want the answers right now. Please give them to me, database. And this is query. The database should now leap into action and do that work for you. Create view. Probably a lot of you know what this is. This is telling a database, hello, I have a query that is so interesting, I'm going to give it a name. And I'm going to introduce you, the database, to this query. We're going to have a nice long-lived relationship with this query. And this is a great hint to the database. Like, I'm going to come back and I'm going to ask about this view over and over again. Please look at it, remember it, anticipate potentially that I'm interested in it. The trade-off here, the intended sort of value proposition, if you will, is that work that is done ahead of time, the work done in response to create view, the work done at data ingestion time, is an ongoing cost as the data change that in some ways is a prepayment for work that might need to happen when you issue a select query. So, a bit more potentially predictable, done in anticipation, so that when a select query comes around, surprisingly, potentially, you have a head start on producing the results there. It takes a lot less time, potentially, to get those answers back that might have otherwise taken, we'll see examples, but whole integer seconds to return, or worse. You've got the answer ready to go, and as a consequence, you can give a much more interactive experience. There's also a really interesting dynamic here in terms of, I guess, economics is the right way to think about it. Rather than redoing the work over and over again in select statements, you're keeping work up to date. So you're doing work in proportion to the rate of change in the data rather than the number of times you look at it. And in the limit, this is really exciting. You can materialize a lot of data with create view statements and then select from them every second. Like just continually watch the data as it spills out. Rather than trying to dial down your use of Snowflake or whatever from hours to days, you go the other direction. You just look at it every second, and it's not any more expensive to do that. So it prompts, hopefully, a bunch of people to think like, well, I'd do something fascinatingly different if they were actually free to ask the questions more and more often. It's important in this framework that we're talking about the same SQL in these two fragments. It's really not great if create view can only do some counts or fairly limited types of things. There's a bit of an uncanny valley where either it's the same SQL, you can both select from it, or take what you're going to select from and materialize it. And if you can't consistently do that, it's just not as useful. So it turns out, in Materialize at least, these are actually the exact same SQL, the same underlying execution engine handles both of these types of queries. The things that will produce the answer for you in the first place, but also then keep it up to date, is the same streaming scale-out data flow infrastructure. All right, I'm going to show a demo. Just to sort of warm you up to what is a streaming database, I'm going to work through an example of a hypothetical use case. It's going to be totally made up, but I'm going to show off what might it look like to do all the work at query time, to maintain it all ahead of time, and why might it be good to do a little bit of both, actually. All right. So in the demo, I'm going to log into Materialize. It just presents as, well, you just go through pSQL. It looks like Postgres. There's a source. I'm not going to create the source. So I had this source running for a little while, and I want all of the data that it has produced. This is an auction data generator. It's got two relations of interest to us, auctions and bids. It's going to produce a lot of them. We'll just do some counts to see how much data is in there. But fundamentally, bids speak about auctions, and auctions have ending times. Let me just pause this for a second so that we can see well, I guess we can see the number there. We've got, I don't know, almost 500,000 auctions, but at any particular moment, if we restrict our attention to the auctions that have not yet expired, it's about 1,000 or so. They turn over pretty quickly in this example just to keep things moving. And we're going to end up with, I don't know, 2 million plus bids or so. And the intent, the use case we're going to put together, you can sort of, if you read ahead on the right side over here, you can sort of see where we're going. We're going to put together a view that collects active bids, so bids associated with auctions that are still in flight that haven't expired yet. We just define a view for that called active bids. Standard SQL, just a join between auctions and bids. And then, pause it here, we're going to take, so hopefully that makes some sense. Bids still in auctions, things might change. These, potentially very interesting to get up-to-date information about moment by moment. What are we going to do with that? We're going to put together a new view on top of that that's meant to be useful to people. And this is, I've called it the outbids relation, but fundamentally anyone who's bid in an auction, currently active, might be interested to see what are the other bids that have outbid me. Who am I competing against? Right? Is there just one other person with a relatively similar bid, or are there thousands of people that I'm competing with, and maybe I should just go find something else to bid on because it's not going to happen. Just another join. So this is a self-join between active bids and itself on the auction ID, where we restrict our attention down to bids. The second bid should have a greater value and be a different bidder. That's the sort of interesting stuff that we're going to try to show back to people and say, like, look, you've been outbid by all of these people. So the plan is to try to offer this up to folks. Bidder shows up, bidder 500 it's going to be, and repeatedly says, show me what's going on with the auctions I'm participating in. Who am I losing to? My mastery of Google Slides is limited. All right, I'll just watch it here for a moment. We're going to do this three different ways. So Materialize has this concept of clusters. Think of them maybe as workspaces, but these are environments where you can set up views. You can just pull data in through select commands. We're going to start with one that's the pull cluster, and this is just going to be running a select, running the entire join pipeline, a bunch of filtering, pulling in all those millions of rows. And you can see in this case, it takes 7 seconds or so. I'm going to say not a great number, or at least you should hope for more with a streaming database. Up to date information, so that's really good. But I'm going to try to convince you that you should want more. Why does it take so long? If you look at the query plan for this, it's big and gross. It does a whole bunch of joins in response to you issuing the query. It's sort of understandable that a bunch of work just happened on your behalf and that it takes some time. So let's do it a different way. Let's go to a different cluster. We'll call this one push. And this is going to essentially put together a data flow materialization for the entirety of outbids. So we're going to create an index here. Just calling it outbids by buyer. So an index on the entire outbids relation indexed by buyer. This will make it very easy for us to show up and say, for buyer 500, what are the results? And if we watch that, should happen. So we'll run some queries here. You can see that instead of 7 seconds, it's taking a few hundred milliseconds. And this is actually an interesting consequence of Materialize providing by default strict serializability as its isolation layer, which if you're familiar with databases, is pretty strong. It doesn't get much better than that. We can dial it down, though, in the interest of performance. So we set the transaction isolation just to serializable. And these numbers will drop down to sub 20 millisecond response times to hand back up-to-date information about who's outbidding buyer 500 in various auctions. Why is it so fast? Here's the query plan now. It's just read the data out of an index. Right? It's not a very complicated query plan. Not much work is happening when you ask the question. We just go and read the data out. Well, that sounds great. Why don't we just do that? Like, why don't we just materialize everything all the way? The problem, if you got your thinking hat on, is that the size of outbids for each auction is quadratic in the number of active bids in there. Every pair of active bids, one of them is visible to the other one. Right? One is an outbidding of the other. which means if you've got an auction with 1,000 bidders in it, there's 1 million outbids elements that are being maintained continually. And that feels sort of bad if no one's actually looking at them. Right? It's a lot of compute that needs to go on, a bunch of memory you need to keep this stuff all resident. Bit of a waste of resources if it's not the case that all bidders are looking at all moments. So we'll do this a third way now, a push-pull way over here, where we build, instead of an index on outbids, we're going to build 2 indexes on active bidders. Active bids. 2 ways, both by, sorry, the video goes faster than I can talk. Both by buyer and by auction ID. And when we go and run queries from there, just give it a moment. It's actually still setting up the data flows, why it takes a few hundred things. It's now on the order of 20 milliseconds to get the results back. Now, why is that? All right, so a very different thing happens in this query plan. Again, thinky hat goes on. If someone shows up and says, I'm buyer 500, amazing, we have an index on active bids by buyer. We can just go and leap and directly get access to their active bids. Each of those active bids names an auction. And we can use, again, the active bids indexed by auction ID to leap directly to the relevant auctions there. We're just leaping around in indexes at the moment. Nothing is scanning data, pulling anything in. All the data are right in memory, indexed exactly the way we need, and it's just looking up information. However, we're only maintaining data. The active bids is linear in the number of input bids as opposed to potentially quadratic, so we can do this with a much lower resource envelope and just do the expansion of the data when someone actually asks. All right, and as a final trick for streaming databases, these are all select queries. They show you answers in response to you typing things and pressing enter. In Materialize and good streaming databases, you should be able to subscribe to these results. You'll get an answer that comes out, as well as a continually arriving changelog saying, at in this case, every second, how have the data changed? And in particular, if nothing has changed, clearly communicate that back out. So this is data streaming in, changing query results, and then streaming all the way back out to, in this case, buyer 500, who's just curious to see, maybe their UI is curious to see, what are the auctions that they need to be paying attention to and the new buyers who've entered the auction. Yeah. So that's a streaming database. And some amount of time explaining, but hopefully that's like, oh, that's fascinating. I'd love to hear more about streaming databases. In particular, you might be, there we go, interested in a few more adjectives in front of the streaming database. So we're going to talk a bit now about scalable cloud-native streaming databases, and there's 2 words I want to call out on here. One is scalable. I think a lot of people, I just want to take a moment to say what I mean by scalable. For a lot of folks, scalable means, I don't know, more computers, more stuff. That's true, more computers will be involved in the story here. But what we're really interested in is more streaming database. So people have potentially had success with their streaming database. So like, this was great, I've got more things I'd like to do with it. I would like to have more streaming database, but in a way that doesn't screw up the streaming database I already have, right? So you want to give people more of the streaming database in a way that's purely additive. If I give you some more computers, and then you turn on a second use case and it tanked the first use case, right? If your query latencies went from 20 milliseconds to 100 milliseconds, that's not good. Like that, thanks for the additional computers and stuff, but my first use case is now broken because of the sort of cross-contamination of all this work. So when I say scalable, I actually really mean figuring out how to give people who want to use streaming databases more and more and more of the streaming database rather than just computers and bytes and stuff like that. The other word on here that's important is A. People want A scalable cloud native streaming. They don't want 27 of them. Like if I just told you here's a different one for each of your use cases, enjoy, that defeats the purpose of having a database. The database exists so that lots of different use cases, users can use the same information, produce results that can be integrated together and more value derived from that. A bunch of different independent silos of streaming databases are not going to solve the problems that organizations have. And that's where the tension comes in, of course. If these things have to work together, but shouldn't interfere with one another, well, the easy solutions go out the window, and we have to start to be a bit smarter. We have to start to have multiple steps. So here's 3 steps. And looking at this, it's sort of painfully obvious this is like a fairly standard picture, actually, for what a cloud data warehouse looks like. There's going to be some differences, though, and maybe we're going to pay attention to the differences as we go. So 3 layers here. These will correspond to the 3 steps that I want you to be thinking about. At the bottom, there's a storage layer. Data arrive into the storage layer. The streaming database records the data there, in particular updates to the data, constant arrival of changes to the data going on second by second. Recorded data are then provided up to a compute layer, and this is where we both compute and maintain these views as the data change. A little different than a conventional data warehouse in that this layer is much less ephemeral. Right? A lot of traditional data warehouses, queries come, they get answered and retired, and who knows, you could just go to a totally different instance next time. The value of this layer is actually in maintaining these views and maintaining data indexed so that it's readily accessible at very low latencies. In some sense, it's the state held at these compute nodes that's important. It's soft state, not hard state, so there isn't a complicated consistency question going on here. But the value is that they're holding onto something, an index representation that's ready to go this very moment. And up top, there's what we call the adapter layer, which is what interacts or interfaces with SQL. The users show up and say, I would like the experience of interacting with a single streaming database. And it provides the facade of that. It coordinates all of the work underneath and coordinates the interaction with each of these SQL connections to make sure that the system presents as if it's just one streaming database that magically everyone seems to be able to use in a consistent and serializable or strictly serializable way. All right, we're going to break this down with a bit more detail now. This is the exciting slide coming up. It's not very different, but ta-da! So this is, and we're going to say, because this is really like the punch, not the punch, but virtual time is a concept got introduced back in the 1980s, 1985, a paper by Jefferson. Many of you may not know what it is. That's totally fine. Not all of us were doing computer science back in the 80s. You may know of it as event time. It's very analogous to event time. Let me explain. So back in 85, it was actually proposed as a database concurrency control mechanism. And the idea was that all interactions with events outside the system, so in this case, data updates, SQL commands, should have timestamps attached to them, virtual timestamps attached to them. And then the system's job now, in essence, is to behave like a simulator, to say like, well, let's imagine that those events did happen at exactly those moments. What should the right answer be? Like if we had some updates at various times and then someone showed up and said, I'd like to see the answer to my query at a very particular time, there's a right answer. Can the system go and compute this now as quickly as possible and just produce that right answer for us? And what this does, which is really nice, is it taking this approach of, great, let's timestamp everything, let's compute correct answers at each of these layers. It provides a really nice boundary between each of these layers where storage assigns virtual times to all these updates, and then its job is to surface them upwards and consistently, repeatedly, durably say, here are time-stamped updates for you, the compute layer, and potentially the adapter layer. The compute layer consumes time-stamped updates, and its job is to pretend as if all of these views updated instantaneously. So to produce output updates whose timestamps correspond exactly to the timestamps in the inputs to the views, and are maintained sort of in perfect correspondence, again, as if in virtual time they updated instantaneously. And then finally, the adapter layer sequences, essentially puts timestamps onto all of the SQL commands that come through to provide the apparent experience of a sequential total order. The timestamps are the things that provide the total order. And with a little bit of finesse, the adapter layer is actually able to provide even more advanced properties than just a total order on all of these events. All right, why do this? I mean, there's lots of different ways that you could go and try to build concurrency control throughout a complicated system. The decoupling is really helpful. So the fact that we're able to design and implement each of these three layers differently is really valuable. The techniques that you use in each of these layers are very different. And the basis on which each of them are correct or performant, very different techniques. And allowing each of them to be implemented separately is just very powerful. You can take experts in each of these domains, throw them at the problem, and the storage folks will use very different techniques to ensure durability than the compute folks will use to get performance, than the adapter folks will use to get the appearance of consistency. What's especially nice about virtual times, though, is that while they coordinate the results, while they make sure that things happen at the same time, they don't actually synchronize them. So they don't force the execution to occur at exactly the same moments. The execution of all of these components are decoupled. They happen as fast as they can happen, which is great. Everyone, the three different sources can all operate at whatever rate they're getting data. No one has to wait for anyone else. The compute layer, if several views are being updated concurrently, they update as fast as they can update. And it's the availability of data, of updates at these virtual times that move the system forward. If you're up at the adapter layer and you ask about something that's good to go, you get your answer right away. And if you ask about a view that is on fire because you did some horrible cross-join, well, you don't get an answer, but you haven't interfered with the rest of the system either. So it's a really powerful decoupler, both from an architecture point of view and also from a performance point of view. At the same time, at the end of the day, you get the experience of a single timeline where all of the events in the system happen on that timeline, and as if there was just one thread running the entire system for you. But it's all, of course, it's all a big lie. But that's the experience that you get. So really, we'll have this slide up a few more times because it's such an important slide. I'm going to talk a little bit about each of the layers just to give you a taste of what goes on in each of them. They're complicated. I said they would be 3 challenging. They are indeed challenging, and smart people are hard at work at each of these layers as we speak. But I hope to convince you that they're tractable. Right? You can work on them and continue to make progress on them, fortunately, without inheriting any of the complexity of the other layers. So the storage layer, the main challenge here is durability. Folks show up with updates from outside the system, and the storage layer needs to make sure to write them down and be able to reproduce them exactly as recorded, arbitrarily far into the future. Data arrive as changed data capture streams. You can think of this as potentially Debezium, a Postgres replication log, various Kafka representations. Basically, folks show up and explain how their data change in a way that is meant to be unambiguous, and we write it down as we see it. When we do that, though, we have some very opinionated things that we do. We put a timestamp on each of these updates. The timestamps have to be carefully chosen in that if data, for example, updated in a transaction, all those updates need to have exactly the same virtual timestamp. Very important that atomicity basically says I should not be able to see half of a transaction, so they happen at exactly the same virtual timestamp, some other ordering constraints. But moreover, so we've drawn a little picture down here of one of these timelines. A time-varying collection is the name that we use for them. You can see a bunch of update events that go on this timeline. Time goes from left to the right. But there's some other important moments here. The boundaries of this green box are important. You're also able to get out of this information 2 frontiers. There's a right frontier, which is sort of the leading edge of where we're currently writing data down. Things at the right frontier, so it's a time. Updates at the right frontier are not yet known. The data may still change at that time and beyond into the future, so it's important, for example, if you're thinking, what's the right answer, to know that I couldn't quite tell you just yet if it's that time or above. Similarly, there's a read frontier that's sort of trailing behind, collecting up all these updates, essentially rolling them up into a maintained snapshot for reasons of bounded memory footprints and bounded storage and efficiency. But this is preventing, if you allow it, but preventing access into the far history of a collection. It's sort of saying any time inside the green region, you can look at, roll up all of the updates there and get the current contents of your particular collection. With those constraints in mind, durability is what the folks here work on, using exciting tools like CockroachDB and S3 and various other considerations. Make sure the data are durable. There are other layers. The compute layer, this is the one that I'm personally most familiar with, is essentially the data flow processing layer. It takes time-varying collections as inputs, does various bits of transformation to them, and produces the corresponding time-varying collections as output. So CDC streams in, CDC streams out that exactly correspond to the input, as if all of these updates happened instantaneously. Just got some pictures. There's a rich variety of data flow operators that allow us to turn any SQL query into a nice streaming data flow. Having done that, there's a few different things you can do with the results. So I've put here in purple, you could have some of these things be an index. This is state that stays in memory in the compute layer and is randomly accessible from the adapter layer up above. It's what gives you the millisecond timescale access to data. But you could also take the results and write them back out to a materialized view. Create materialized view is a command that we'll see in just a moment. It puts the data back in the storage plane, which allows people in other compute instances to pull the data in. So for example, if you're the first step in the data pipeline, you're cleaning things up, you're doing some denormalization, who knows what, you might have a whole bunch of downstream consumers that you don't want in your address space. Like they're doing crazy stuff. You don't want them to crash or slow down your work, which is important to lots of people. So it might make sense to write the results of your views out to the storage layer and have other people bring that data back into their compute environments that are isolated away from yours, where a materialized view would be relevant. But other than that, go as fast as possible. Like be as efficient as possible, use as little memory as possible, go fast. Durability is not a problem here because of the deterministic nature of all these operators. Determinism is what provides the correctness guarantees that we need here. All right, last layer, and this is a bit of a thinky one, is the adapter layer. And fundamentally what happens here is those SQL commands that came in need timestamps. Right? We've actually got 100 people connected all saying select this, insert that, create whatever. We need to put timestamps on these commands, and the timestamps that we choose for those commands are what determine the apparent behavior of the entire system. And the people observing the system are the folks connected through these sessions. So if you just put timestamps on commands, actually a good thing happens already. You get serializable isolation. The timestamps themselves and our correct behavior in response to them are n order on all of the events. It's not so bad, though it turns out if you're familiar, serializable isolation has a bunch of really weird properties that you would like, no, that can't be true. But the order doesn't need to correspond to real time. And you would really like that in a lot of cases. You'd really like if you go and insert some data into a table and then read from the table that maybe you should definitely be seeing what you just inserted into there. And to get this property, you need something slightly stronger than serializability. Something that's sufficient is strict serializability, that timestamps need to increase as real time moves forward. So there's a few constraints that this layer has in terms of installing timestamps. That's one of them, strict serializability. There's some others, though, just to throw up. If your query, let's say it involves a table from the storage layer and an index from the compute layer, there are these read and write frontiers there. And for example, for a timestamp to be valid, it needs to be at least as big as all of the read frontiers. Right? If that's not the case, we're not sure they're actually going to give you correct data out. So you have to pick sufficiently large timestamp to get correct results. But you might also want it to be prompt, right? The result might want to, you want to come back right away. You want to pick a timestamp that is not greater or equal to any of these write frontiers. And if you do that, you're in a position to get your result back pretty much right away. Certainly you don't have to wait for things to happen. You might want it to be the right end of this timeline to get the freshest of possible results. But that's a little bit in tension with strict serializability, which says things only have to go to the right. So if you go all the way to the right, you've ruled out a bunch of options for the next person who asks a question. It's complicated and challenging. There's some fun trade-offs here to provide a great experience to everyone that totally conceals the fact that actually there's 57 different computers doing different things all at once. So their challenge here is consistency, providing the appearance of consistency across a whole bunch of fundamentally independent things coordinated only through virtual time. All right, this slide, like I said, here it is again, super important. So, conventional 3 layers of a cloud data warehousing type thing, but coupled through virtual times, we're able to have things continually change, continually update without losing our heads, without just utterly losing track of what's going on in the system. So what I'd like to do now is show off a little bit of the scaling aspect of the scalable cloud native streaming database. So there are a few things I said you're going to want out of such a thing, and I'm going to show off 3 of them that I think are pretty cool that you wouldn't get if you just put Materialize onto a one computer and sort of said, good luck, enjoy. So we're going to look at the same setup as before. The left pane over here is going to be that same streaming updates on that push-pull cluster that are going to show us all the changes to outbids for buyer 500. It's really not going to change throughout the course of the demo. So the only thing to notice on the left side of the screen is that stuff's happening. As long as it continues to happen, you should be pretty happy. And I'm going to do most of the action over here on the right side. The first thing we're going to do is just try to make a mess out of everything. So we're going to head on over to the pull cluster. You might remember that was the place that queries go slow, right? Because we have no built indexes. We're just rerunning stuff from scratch. And we're just going to start to ask a bunch of questions over there. Basically, take many integer seconds to get answers and observe that that does not contaminate the interactive experience that's going on over on the left-hand side. The left-hand side still continues to tick at the same rate, even though the right-hand side has decided I have 10 seconds worth of work to go and actually do. You can isolate the performance, maintain low latency properties on one, and allow analytic work to occur concurrently without jumping the queue or getting in the way of the interactive experiences. Anyhow, demonstration number 1. Ta-da! All right, great. No, we'll do applause in the question section later. The other thing that we might do, and this requires just a bit of explanation, these clusters, these workspaces, can be backed. They're backed by compute resources, of course, but they can be backed by multiple replicas of the same same work, essentially, different compute resources. So what we're going to do here is take the push-pull cluster, the thing that's powering the left-hand side, and give it another replica. Just give it we're going to scale it up. It's at a small replica now. We're going to give it a medium replica. And we've gone and created that, and it just stitches itself in. There's a notice that comes back, but otherwise just stitches itself in and is supporting the first replica, which, sorry, I apologize. I should have warned you to watch for this, which we just dropped. So there's only one replica running now. It's a medium replica. And there was no interruption over on the left-hand side. Yeah. So we just rescaled from a small cluster to a medium cluster while maintaining this interactive experience with no interruption. Right. This is one of the really powerful parts of compute being decoupled but still coordinated through virtual time. These two compute instances were doing exactly the same thing, so we could deduplicate the results. And as long as one of them is live and running, we're getting fresh results spilling out, even as we fiddle around with which one is backing it, what's the scale, all those sorts of things. Now, what we're about to do is drop the medium cluster. So now there's no replicas, behind this cluster is not running anymore. It's stopped. And you might say, oh, that sucks, but actually a good thing is happening over there. I mean, as good as it can be when you don't have any computers to do your work. But the stream that's coming out has paused. It knows that it does not know the answer to how the data changes in the next second. So it's holding its fire. It's not going to tell you, yeah, I don't know, probably nothing happened. No, it's just waiting until it actually gets the information that it needs. And we've reprovisioned a small replica behind it now, just to cut back over. And as soon as that comes online and gets hydrated, it'll pick up exactly where it left off and actually backfill all of the changes in the sort of 10 seconds or so for which we had no compute resources. So even in the case of failure or deprovisioning, you actually get the right information out. And it's a behavioral hiccup, like there's some time that passes, but you don't get the wrong data coming back out of this. So you can, without having to change your application, just rely on getting correct information slower or faster based on the machines you have. All right, that was trick number 2. Trick number 3 that we're going to do is hop onto both on the push cluster and on the pull cluster, so the two not push-pull clusters, create materialized views that select out of the outbids relation. So we've got output 1 and output 2. Output 1 is the pull cluster. Output 2 is from the push cluster. These are the same view computed 2 different ways on 2 different computers. The pull way has no indexes, so it's pulling in all the work and doing it over and over. The push one is reading out of an index and writing it back into storage. And what I've said, hopefully you believe me, is that these are the same. And so what we're going to do now is actually subscribe to the query that says, show me what's in the first one but not the second one. And that's what's happening right now. You are seeing all of those changes, which isn't necessarily convincing until I go and I put those progress statements back in. So that Materialize not only doesn't show you anything, it confirms second by second there is nothing in there. There's no millisecond at which there's a single record in one of these relations and not in the other one. And that will be true forever. These things, barring bugs on our part, these things are exactly equal. Virtual time is keeping them perfectly coupled. If these were 2 separate use cases, for example, like you had one team that was figuring out who are the auction winners, how much money should we collect from them, and another team that was producing whose auctions have closed, we should give them some money, those numbers will always match perfectly. The imbalance between those dollar amounts will be 0 for all time. And this is really powerful for teams building low latency applications, 2 different people doing 2 different things and then bringing their data together and having the guarantee that it is as if their work was executed instantaneously, simultaneously against the same data. There's no more trying to figure out whose data are slightly out of date and patching that up with various bandages. Great. So this slide again. It's the last time for this slide. Just to recap, because like I said, it's super important. The 3 steps that we have here are storage, compute, and adapter, and they're coupled through the use of virtual time. This is, again, a really powerful, really not fundamentally complicated coordination primitive that allows us to reduce the complexity in the overall system into challenging steps for sure, but ones that are tractable by folks who are expert in each of these domains. And allows you to give this experience that, I don't know, increasingly I think is really cool. Just all of the really impressive stuff that you can do spinning up whole bunches and compute teams of people who don't even know about other people's existences using the results of their data products back through the storage layer and not having to reason about all the complicated stuff you'd normally reason about in a system with so many moving parts. Yeah, this is what I have for you. So we're going to end here.